So we're going to start the acid-base unit with a lot of the ideas that you learned during first year chemistry, just kind of reviewing some properties, pH, that kind of thing. So these first few slides we're going to go through pretty quickly. So properties of acids. Remember that way back when you learned that an acid was something that will produce H pluses when you put them in water. Last year, hopefully, you learned that in addition to just talking about H+, we talk about the hydronium ion, which is really a water molecule with the H+ attached to it. So instead of the H+ floating around freely, hydronium is a water molecule with that H+ bonded to it. Bronsted-Lowry definition, again, is something that we introduced you to during first year. An acid, according to Bronsted-Lowry, is a proton donor, something that can give an H+ up. Arrhenius and Bronsted-Lowry pretty well coincide in terms of definitions. Identifies the same thing. It's when we get to bases that you see that it's a little bit different. All acids ionize to give a proton. So acids are not necessarily ionic. Most acids are actually molecular. But what they do is the H+, the bond between the H and the O, or the H and the other atom, is polar enough that the electrons get pulled towards the other atom and the H+ is removed. Remember that acids have pH that are less than 7. They turn litmus paper red. They taste sour. Think about orange juice and vinegar. They are electrolytes. When you dissolve acids in water, they produce H+ and whatever the anion is. Couple of properties. You might have seen these last year. Acids will corrode metals to create hydrogen gas or the metal ion or some kind of gas. It's not necessarily always hydrogen gas, but they will corrode metals. They'll cause metals to become ions. Acids will react with sulfides to produce H2S. That's the smelly gas of rotten eggs that you think of. And acids will react with carbonates and bicarbonates. You've seen this a couple times, to produce CO2 in water. And finally, the most obvious one, they react with bases to form salt, some sort of ionic salt, and water. So some common acids that you have worked with or have seen probably. HCl, hydrochloric acid, is what you find in your stomach. Sulfuric acid is what is in car batteries. Acetic acid, hydrogen acetate, is what you have in vinegar. Citric acid, this formula, what you find in citrus fruit. And ascorbic acid is what vitamin C is made out of. Let's shift gears now and go to some base properties. If you need to, pause the video so that you can get these properties down, or you can just go to the PowerPoint on the website and look at the slide without any audio. All right, so according to Arrhenius, bases increase the OH- concentration in water. Bronsted-Lowry is a little bit different. Bronsted-Lowry says that a base is a proton acceptor. So an acid is willing to give up an H+, a Bronsted-Lowry base is willing to accept an H+. So that's a little bit different than what the Arrhenius definition is. The result oftentimes is the same. You have an H+, you have an OH- increase in water, you have an H+ decrease in water. But the way it's approached is a little bit different. Ionic hydroxides will dissociate to produce OH- ions. So there's the Arrhenius definition, but there's also the Bronsted-Lowry definition. Molecular bases, which oftentimes you're going to see them, they contain nitrogen, are going to react with water to produce OH- ions. So the proton acceptor is kind of a modified version of the molecule that you see as a result of the molecule reacting with water. So you put something that is basic in water, and what it will do oftentimes is it will react with water take on the H plus, accept the proton, and then what's left of the water molecule is an OH minus. Bases have pHs that are greater than 7. They turn litmus paper blue. They typically taste bitter or chalky. Coffee and cocoa are examples of some bases. They are likewise electrolytes, just like acids. They react with acids to form salts and water. And they feel soapy or slippery because they will react with fats and oils in order to produce soap. So you spill a base on your hand and they feel slippery because they're reacting with the oils on your skin. Some bases, probably not as familiar with bases as you are with acids. Sodium hydroxide is called lye. Oftentimes in the spring you need to change the pH of your grass, and people will throw lye on the grass to change the pH of their grass and make it healthier. Potassium hydroxide is known as potash. Barium hydroxide is used in a lot of plastic productions. Milk of magnesia is magnesium hydroxide. That's an antacid that they still sell to this day. Maalox contains the base aluminum hydroxide. Again, it's an antacid. When your stomach is producing too much H+, you take an antacid, a base, in order to change that. And then probably the base you're most familiar with is ammonia, NH3. All right, so let's take a look at definitions again of acids and bases. We had them in our list, but let's look a little more closely. So acids produce H pluses or hydronium ions. Bases produce OH minus ions. The problem is you look at the formula for a base and you don't always see the OH minus. So for Arrhenius, the definition of bases is a little restrictive. So we go to the Bronsted-Lowry definition, where you have a proton donor or a proton acceptor as an acid or a base. And then remember that a proton is really just a hydrogen atom that's lost its electron. We can pull in a lot more bases than we have been able to under the Arrhenius definition. So ammonia, according to Arrhenius, would not be a base because NH3 doesn't have an OH. But ammonia will be a base under Bronsted-Lowry because ammonia, NH3, will react with water to produce NH4+. The NH3 accepts the proton and leaves you with OH minus ions in solution. So Bronsted-Lowry bases are a little bit more challenging. So here you can see to be an acid, you have to have a particle that has an H+. You have to be willing to donate an H+. So in this case, HCl will donate an H+ to water. You get hydronium ion, and you're left with Cl-. Not sure why they've made this size so much bigger than that one. Bases, here's the example that I mentioned before. A base is a proton acceptor. So NH3 has a pair of electrons sitting up here. It will accept an H+ from the water and become NH4+, and what's left over? OH-. So the OH- causes the pH to increase. The H+ concentration goes down because it's bonding with NH4+. So that leads us into the idea of conjugate pairs, conjugate acid-base pairs. The pair differ by a proton. So the acid has an extra proton, whereas the conjugate base does not. So here we've got an example that's not typical. So I'm starting out with HCO3- as my acid. It has an H that it's willing to donate. Its conjugate pair is that same structure without the H. So notice the only difference between these two are an H+. The acid has it, the base doesn't. So the acid is going to donate an H+ to a base. In this case, water is acting as the base. It's going to donate an H+ to water. Water becomes H3O+. So now it has the extra proton. Comparing these two, the H3O+ is the acid, the H2O is the base. This is the base pair, or this is the electron, wait, this is the proton acceptor, this is the proton donor. So these two are conjugates, base, conjugate acid. Typically, we talk about the conjugates as being the product. So this is the ACE, this is the acid, this is the conjugate base, this is the base. On the product side, you see the conjugate acid. And again, notice their formulas, they only differ by an H+. So let's take a look at a couple of examples, see if you guys can identify things. This is one we saw before. Oops, that should be H3O+, not H2O+, there's a typo. HCl reacting with water to produce Cl- and H3O+. What's the conjugate acid? What's the conjugate base? What's the base? What's the conjugate acid? So can you figure it out? Take a moment, think about it, and here come the answers. So here's my acid, here's my base. Conjugate base is a hydrogen ion different than the acid. Conjugate acid is a hydrogen ion different than the conjugate base. And again, that should be an H3O+. Okay, next one. What do you got? What's the conjugates? What are the pairs? Can you identify them? Here are the answers. So water is acting like the base because it's going to accept the H+ from H2SO4, which is the acid. HSO4- is the conjugate base. They are identical except for an H+. These two things are identical except for an H+, so they are conjugates of each other. You can also have molecules that are amphiprotic, which means that they can act both as an acid or a base. Notice in the examples below that water is doing both things. In this first reaction, water is acting as a base. It's going to accept the H+ from HCl. So it's acting as the base here. But with ammonia, ammonia is acting as the base. Water is going to act as the acid here. So water is going to be donating an H+ to ammonia, whereas HCl is donating an H+ to water. So water, in this case, is amphiprotic. Sometimes you'll hear it referred to as amphoteric too. They mean the same thing. All right, so let's talk about relative strengths. If you have something that is a very strong acid, its conjugate is not going to be a strong base at all. As a matter of fact, it's going to be not a base whatsoever because it doesn't want to accept that H+ back. So HCl, if you have something that's willing to give up its H+, its conjugate is not going to take it in. So strength-wise, we talk about it being negligible. As the acid gets weaker, the conjugate actually starts to have more of an impact. So you have the H+ traveling back and forth between these guys in this area because depending upon what they're reacting with, if they're reacting with something stronger than themselves, they're going to take in the H+ or give up the H+ depending upon what's going on. Likewise, if you have a very strong base, it's going to be something that's not going to, its conjugate is not going to act as an acid. So O2- takes in H+'s very easily. Its conjugate, HO- or hydroxide, is not going to give that H+ up very easily. So this is a very strong base, but its conjugate is irrelevant in terms of being an acid. So just the opposites. You're going to see more of this stuff when we start taking a look at equilibrium reactions. But I just wanted to start pointing that out to you, that if you have a strong acid, its conjugate is going to be weak, non-existent. If you have a strong base, its conjugate is going to be weak, non-existent. It's the substances that are weak that actually are more interesting to look at because they can do both things. They will donate or they will accept H+'s depending upon the situation. All right, so how do you predict the position of that proton transfer? You've got to consider which acid or base is stronger. So you've got a situation here where you've got a very strong acid. Water, not very strong in terms of